Hi everyone, welcome back. Today we're exploring the Black-Scholes model. And the Black-Scholes model, also known as the Black-Scholes Merton model, this is jargon, but in this case, this is a model that is commonly used to predict the fair price of an European call or put option. So an European call or put option is an option which cannot be exercised before the expiration date. So there are some assumptions here, as you might guess. So to our audience, you might be asking, okay, so what are the inputs to the model? What does it use to predict the fair price of a given call or put option for an European stock? So in this case, there's 5 inputs. There's the strike price. The strike price of an option represents the price at which a put or call option can be exercised. The current stock price is pretty simple. That is the price of the current stock. The time to expiration. Every option is a contract and it has an expiration date. So this is pretty much the number of days to expiration divided by 365. There are variants like you could technically change that to do that in days, but that's a different thing. And in this case, that's also the risk-free rate. So what is the risk-free rate in Black-Scholes model? I'm not too sure about that, but in this case, it seems that the risk-free rate is the rate used to discount the exercise price in present value calculations. The larger risk-free rate offers the present value of the exercise price, which increases the value of an option. Okay, I don't think I really understand what that means, but let's take a look at that. So as you can see, I'm really new to this. It's my first time seeing this in quite some time. So there we go. So it looks like we have talked about the current stock price, the exercise price, expected term. So expected term in this case is pretty much the time to expiration and the risk-free rate. So what does this mean? Difficulty to determine. So apparently it's really nice that this IPOHub even listed how easy it is for us to get that. So in this case, the risk-free rate is easy to find online, but the exercise price is discounted by risk-free rate. So a larger risk-free rate causes the exercise price to be smaller. And thus the fair value of the option to be larger. So I think risk-free rate is the interest rates, I guess. Yes, that's why you can find it at the Treasury's website. Is risk-free rate the same as interest rate? The risk-free rate of return is the interest rate an investor can expect to earn on an investment that carries zero risk. So that is if you borrow money from the bank. Okay, I guess that makes sense now. And the volatility is a more volatile stock is more likely to expire in the money. So higher volatility causes the value of an option to increase. Okay, yeah, I'm pretty curious how they would value volatility then. And the dividend yield. So in this case, it seems that this IPOHub seems to show a different variant of Black-Scholes. In this case, there are 6, but over here there are 5. But it's okay. It could be either, like we could use either. So let's keep it with an open mind. And specifically in this case, like we are not using the dividend yield here in this case. So we can see that there is no dividend yield inside this definition of the Black-Scholes model. But it's okay. So our strategy for today is to watch Jonathon from Quantpy explain the Black-Scholes implementation in Python. So we'll be standing on the shoulders of Jonathon, and we will see how we can implement this in Python. So with that, let's get started.
Hello and welcome back to ASX Options. This is Jonathon speaking. Today we're going to be implementing the Black-Scholes formula in Python. So let's just get started. So we're going to add a new file. I'm using the Visual Studio editor, but you could use whatever editor of Python you want. So let's just go ahead, create a new file, blackscholes.py. Okay, so we're going to be implementing the Black-Scholes formula in Python. So the first thing we're going to want to do is import NumPy as NP, okay, and we're going to need scipy.stats, or from scipy.stats we're going to import norm, because we're going to need the normal distribution. So let's think about the parameters that we used in our Excel video. So let's just replicate them. So define variables. So we had our interest rate, which was 1% or 0.01. We have our underlying at $30. Our strike price was 40. And
okay, I don't like those variable naming, so let's take a step back here and let's create our requirements.txt file. Our objective now is to keep up with Jonathon here, and let's install some dependencies first. What I'm going to do is I'm going to create a virtual environment, and I'll be installing the latest version of SciPy. And afterwards we'll be defining the same variables, but we will leave comments to remind ourselves what exactly are those variables. So let's install it by installing our requirements.txt file. In this case, it only contains SciPy. Seems that we're using 1.10.1 as of 4th March 2023. So let's import, oh yes, of course, we need NumPy. So I'll have to run this command again in a bit. So import NumPy as NP. From SciPy stats, import norm. So in this case, we'll be using the normal distribution in Black-Scholes model. So I'm not too sure like which variant is Jonathon here going to use, but it's okay, we'll figure that out in a bit. Next thing, let's define the variables. In this case, R in this case is the risk-free interest rate, if I'm not mistaken, and S in this case is the, I think S is the current stock price, and K is strike price. Okay, let's carry on.
And time was 240 days. Remember, that's out of 365 variables. So we had our interest rate, which was 1% or 0.01. We have our underlying at $30. Our strike price was 40, and time was 240 days.
That's the time to expiry. So in this case, time to expiry. So this is a float, this is an int, this is an int, and this is a float.
Remember, that's out of 365. And we also had our volatility, or our sigma, which was 30%.
I'm not too sure what exactly is this sigma here. So this is the volatility, and Jonathon set it to 0.3, but I'm not too sure what does this 0.3 here means, like from a qualitative perspective. So borrowing from US Treasury. Sorry, I mean lending interest from lending from US Treasury, I guess. Money to US Treasury. This is the current stock price, and this in US dollars, I guess. And in this case, oh wait, but because this is in euros, so it should be in euros. Options, time to expiry would be days divided by 365 days. And volatility, there's a to-do here. Discover, like, understand how this is derived. Okay, let's continue.
Okay. So let's create a function, because then we're going to be able to use it again and again and again. So let's call it Black-Scholes, and we're going to take those inputs. R, S, K, T, sigma, and there's one more thing. We need to tell it which type it's going to be. A call or a put. So I'm going to call that type, and we're going to say that if we pass the string C, it's going to be a call, and if we pass the string P, it's going to be a put.
Okay, so at this point, we might have different variants of the Black-Scholes model. So I'm going to create an abstract Black-Scholes service. Black-Scholes service is going to be an abstract base class. And to our viewers, to our parrots here, it's optional for you to abstract it to a service. In fact, for the purposes of learning, I would agree with Jonathon's perspective here to just define that method and use that. But in this case, like, to our parrots, you might be asking, okay, then why would you create an abstract base class here and use this in this case? More for abstraction purposes and to give ourselves the ability to develop multiple implementations for this. And but regardless, I would think this is a good to have. So I'm currently calculating defining a calculate method. Abstract method, static method, abstract method. Okay. So in this case, this calculate method is used to calculate the Black-Scholes model. So in this case, it's to calculate the price of a given European call option. So used to calculate the fair price of a given, let me increase this, call option. Okay, so service responsible for calculating the fair price of a given European call put option. We can have multiple implementations for this, so we make this abstract. We can extend off this interface, this abstract base class, to implement a new variant. Okay, so for calculate in this case, according to Benjamin, he mentioned, sorry, is it Jonathon or Benjamin here? Let's, oh sorry, is it? Quantpy founder Jonathon, I'm so sorry, it's Jonathon. So Jonathon mentioned here in this case that calculate has a few methods, a few inputs here. So here is the risk-free. Let's just define this risk-free interest rate. Risk-free interest rate, this is a float. So something like 0.01. That's also the current stock price. This should be a float really, right? Because the price of the stock can be in cents. So this would be 0.1. This is 30.00, something like this. Then there's a strike price, as well as there's a time to expiry, and that's the volatility. So we have a simple method here. Let's see. Yeah, okay, looks about right. Okay, now let's create a simple Black-Scholes service implementation, and let's extend off this interface, and let's start overriding the static method. So let's copy this here, and there we go. Now we will continue off Jonathon's tutorial.
But let's, by default, make it equal to C.
There's one last thing I forgot, which is define a simple enum here. Let's call this options enum. And this represents the possible option types that we have. So it can either be a call or a put. So let's define this inside our interface as well. Option type, option enum, call, put. Okay, let's continue.
So what are we going to do in this function? It's always good to define what you're going to do. So if someone's reading over your code, they can see clearly. We're going to calculate the Black-Scholes option price for a call or put. Cool. So the first thing that we're going to define is D1 and D2. So D1 is the natural logarithm. So np.log of S over K plus the interest rate plus sigma squared. So Scholes.
I'm not too sure what D1 means here, so I'm trying to recap that.
Option price for a call or put. Cool. So the first thing that we're going to define is D1 and D2. So D1 is the natural logarithm.
What does natural logarithm mean? Okay, I'm not too sure what does this mean. It's such a terrible name. Understand what exactly this term means. So yes, we do have a formula, but in a human readable way, like what does this mean?
So np.log of S over K.
So it's the log of natural log of strike over current price equals to natural log of S strike price divided by current price. Okay, so I'm abstracting each term out of D1 so that it's more readable. Let's call this net log strike to current price. Okay.
Plus the interest rate plus sigma squared divided.
Why would you add the interest rates with the volatility?
Divided by 2. And this is what I forgot in the Excel. You have to multiply that by the time.
Okay, not sure what that means, but okay, let's accept that for now. But let's set this to be equals to net log of strike to current plus risk-free interest rate plus sigma multiplied by time to expiry. Okay, nice. It looks like ChatGPT actually managed, no, sorry, in this case, this is just my copilot here. But in this case, we were able to get the formula easily here. So D1 in this case is the natural logarithmic term. And that is consisting of two terms. The first term is the natural log of strike price over current stock price. Okay. And we add that with the risk-free interest rate. And together with volatility squared divided by 2. And we multiply it by time to expiry. Why though? Why would you make it so complicated? There must be a reason why, but it's okay. Let's continue.
So let's divide that entire thing by sigma times by np dot square root. So the square root function you can get from math, but I'm using the numpy square root. Could just have easily squared it to the half. So now pretty comfortable that
well, I'm not comfortable, but okay. This, I mean, it's understandable. This is not an easy formula or model to understand. So this is a numerator term. I'm going to abstract it separately, otherwise it gets a little bit too hard to understand. So in this case, the denominator is the volatility multiplied by the square root of time to expiry. Okay, let's accept that for now first.
That's our D1. So let's go ahead and define D2. And if we remember from last time, it's just D1 minus sigma times by the square root of time.
Okay, let's define D1. D1 is just D1 numerator divided by D1 denominator. And D2 is the volatility term of the Black-Scholes model. Okay, actually, let me see what time term of the Black-Scholes model. And D2 is the volatility term of the Black-Scholes model. So why is this time term? I guess technically it's kind of the time term because the strike price, sorry, the current stock price is related to current stock price is technically related to time. And for this, okay. I guess that kind of makes sense. So the time term contains stock price, risk-free interest rate, volatility, and time to expiry. Technically, they are all related to time. But D2 is a separate volatility term, and volatility is related to time. So perhaps, why would you call this a volatility term then? But okay, D2 in this case is equals to D1 minus sigma minus volatility multiplied by square root of time to expiry. Well, technically the volatility term is related to time, but okay. D2 is a variant of D1 and they subtract it by volatility multiplied by the square root of time to expiry. I don't think I really understand exactly what D1 and D2 means at this point of time, but I will accept it for now and leave it to Jonathan to explain it for us.
Okay, excellent. So now we have to take into consideration whether it's going to be a call or a put. And we also want to allow for the scenario that some of the values are coming in incorrectly. So we're going to do a try and exception. So we're going to try if the type above is equivalent to C, then it's going to be the call. So we're going to call that the price. If you remember, if it's a call, it's the underlying price times by the normal distribution. So norm dot the cumulative distribution function, and we just have to type in D1, centered around 0, and because it's the standard normal distribution, we have a very standard deviation of 1. So minus the discounted strike price, so NP dot exponential minus R times T, so that's the discounted strike price times by norm.cdf D2 centered around 0 and 1.
Let's take a look at the documentation for a bit. So if the option type is equals to option enum.call, then the price, which I assume is a float, is going to be equals to current stock price multiplied by, okay, current stock price multiplied by normal distribution of D1. Okay, so let's take a look at D1's function signature. Cumulative distribution function of the given RV. So X is the array-like quantiles. So that is D1 in this case. And you know what? That documentation is pretty bad. So let's take a look at SciPy stats norm cumulative distribution function method. Okay, let's take a look. Okay. So the profit density function is the exponential of negative x squared divided by 2 divided by square root of 2 pi. It's very technical. I don't think I really understand what this formula really inherently means, but this is probably a probability density function where if you pass in a number, it gives you back another number within the distribution. So the first parameter to this is okay, 0 is the mean and scale is the standard deviation. So okay, so D1 followed by log equals to 0 and scale is equals to 1. I know they are the defaults. Yes, it is the default, but for readability, I'll just leave it like this so that we know that log is the mean of the normal distribution cumulative CDF. Okay, so this is around 0 and scale is the standard deviation here. And let's come back to this. So minus strike price multiplied by numpy square root, numpy exponential negative risk-free interest rate multiplied by time to expiry multiplied by the normal distribution of D2 again. It must have took the creators quite some time to arrive at this formula, but we are really fortunate that we're standing on their shoulders, man. Like, I can't imagine them having to come up with this formula by themselves. Okay, let's continue.
Excellent. So now I would say else, but let's just else if type is equal to P, then the price of the put is going to be equal to the discounted strike. Forgot the NP there. Discounted strike times by the normal distribution of minus D2, centered around 0, variance of 1, minus S times norm dot CDF of minus D1, 0, 1. Excellent. So that's our try, and let's make our exception. Okay, so when are we going to accept this? So if something goes wrong, what do we want it to print back? Let's say, okay, let's assume that you've typed in near the C or P, or you've made some kind of mistake. Let's just say, please confirm all option parameters. Parameters above. And 3 exclamation marks, because why not? Excellent. And we can't forget to actually return something. So under the try, if we've calculated a call price or a put price, let's return the price of that option. Excellent. So let's test this out. So we're going to print option price is, and I'm going to round it because it'll have infinite amount of places. So Black Scholes, and remember we've defined these parameters above. So we've actually called them exactly by the name. So let's just copy and paste them. Okay. And because we're using the round function.
I think Jonathon really, it was a really good demo by Jonathon. And yeah, it's just that I guess that was a demonstration, so I don't think Jonathon was really focusing too much on the implementation details. So I think that's totally fine for a demo. Price is equals to strike price. So this, we're currently calculating the price for the put option here. So strike price multiplied by the exponential of negative risk-free interest rate multiplied by time to expiry. I should really put them side by side. Oh, that's so hard to see. Okay, let's do this. Okay, that's even harder to see. You know what? Let's bear with it for now. Okay. How do I? Okay. Okay, so price is equals to strike price multiplied by K. Sorry, strike price is K, multiplied by exponential of negative risk-free interest rate, multiplied by time to expiry, multiplied by the distribution function of D2, negative D2, minus current stock price, multiplied by the cumulative distribution function of negative D1. Okay, else raise value error, invalid option type. In this case, we return the price. So that's it. I think the Black-Scholes model is more difficult because of the terms. I don't think it's really hard to come up with this formula. It's just that understanding this formula is probably the harder part. That said, I don't think we have to really necessarily understand every single term in this Black-Scholes implementation for now. I'm assuming that through using this model more and more, we should develop a good intuition for how exactly this Black-Scholes service work. So now I have option type here. And we are now going to calculate the fair price given these variables here. So let's try running this. Okay, risk-free interest rate equals to R. Okay, current stock price equals to S. Strike price equals to K. T is time to expiry. Okay, T. Sigma is volatility, and finally option type. So there we go. I am giving the inputs to this Black-Scholes service implementation as a key value pair so that it is easier for us to know, to read this, right? Like we might accidentally pass in the current stock price as K or vice versa. So now that we have this, let's calculate the fair price and let's print this. So Python 3 main.py. Okay, I think I made a mistake. To be specific, abstract method should be below static method. So now our fair price is -7. Maybe we have a bug here somewhere. Why would the fair price be -7? Okay, let's see. Let's see what Jonathan gets.
And here, because we're using the round function here, we're going to round 2 decimal places. Finish off the brackets, save that down. Now in our terminal here, we're going to type Python Black-Scholes py, and we're just going to hit run. Oh, and no module SciPy. So for any of you that have that, we're just going to pip install those modules. Super easy. I just didn't have that in this environment. But NumPy must have been there. So we'll just wait for that to install. And then we'll be able to run that again. So just up key, enter. Excellent, option price.
Ooh, okay, so this is expected to be 0.51. So I must have messed up somewhere. So D1 is equals to NumPy log of strike price divided by current stock price. Sorry. Did I flip it? S is the current stock price and K is the strike price. So it should be current stock price to strike price. And that explains it. So it should be current stock price to strike price. That explains why. Okay, so let's try running again. And okay, we got 0.4899. But that's not exactly what Jonathan got either. So let's take a look closer. We divide it by... Sorry, we add it with the risk-free interest rate plus sigma squared. I don't think this is the reason why it's different, but I will be more particular with the brackets here. So volatility, sigma is volatility, right? Yes, sigma is volatility. So volatility squared divided by 2 multiplied by time to expiry. So that's the numerator. And the denominator is sigma, which is the volatility, multiplied by square root of time to expiry. And we take numerator divided by the denominator to get d1. And d2 is d1 minus volatility multiplied by square root of time to expiry.
Do a try and exception. It's going to be the centered around 0. And because it's the standard normal distribution, we have a very standard deviation of 1.
So S is the current stock price. Okay, nice.
So minus the discounted strike price, so NP dot exponential minus R times T. So that's the discounted strike price times by norm.cdf D2 centered around 0 and 1.
Okay, so discounted strike price is equals to the strike price multiplied by the risk-free interest rates multiplied by time to expiry. So this hopefully makes it more readable. And it's the same for our discounted strike price here. So strike multiplied by this. Okay, so since both terms are going to use that term, let's put it outside of the if here. And this would be used here as well. Okay, so this should be more readable. And the idea behind the discounted strike price here is that the strike price is really cheaper if the risk-free interest rates are higher in this case. Or is it lower? So this is maybe I should abstract this to a separate method. Static method discounted strike price. Strike price equals to float. And that's the risk-free interest rate as well as the time to expiry. This gives back a float, and this is strike price multiplied by risk-free interest rates multiplied by time to expiry. The reason why I'm extracting this is so that we can better understand each of these terms separately. So for example, if I wish to understand how the discounted strike price changes with a higher or lower interest rate, so let's say I do, let me comment this out, and let's say I'm interested in the discounted strike price at, let's say, 0.0 at 1% interest rate. This would be strike price, so in this case it's K. Risk-free interest rates would be 0.01, and the time to expiry would be T. So we can print this, and let's say if I wish to see how that would change at 2%, then this would be like this. And let's say we want to know how the strike price has changed versus the discounted strike price here. Let's print out K here. And now if you run python 3 main.py, oh, I can hardly see the difference, but it seems that the discounted strike price at 1%, or let's make it more dramatic. Let's try printing it out at like 10% here in this case. we can see that the discounted strike price at 10% risk-free interest rate is much lower. And that makes sense because if the risk-free interest rate is higher, then it's cheaper to exercise this call option here. So that's, I mean, like, it's easier to exercise it, so that's why it's lower. Okay, let's see. Calculates the discounted strike price given interest rate and time to expiry. So why is it that counted? It's paid and I just need to discount it to the present value. Okay, I guess the codex model is if we exercise in 1 year, the 40 euros later can be counted as worth $38 euros today. So the second question is that why is the strike price discounted with respect to risk-free interest rates? So because the strike price is paid at the end, we exercise in 1 year, 1% is I don't think this term really makes sense to me, but let's see. We saw that strike price. So next is how does the discounted strike price change if risk-free interest rate increases? So if it increases, that's not, yeah, it actually decreases here. So I think Codex actually got it wrong here. So for example, when we passed in 1% interest rate, the discounted strike price was at $39. So given K equals to 40 and T equals to 240 divided by 375. Okay, discounted strike price at 10% is actually lower than the one at 1%. Okay, so let's do the same experiment. And this time we keep the discounted interest rate at 1%. But instead we set the time to expiry here to be, let's say, 100 divided by 300, and oh, that explains the difference between us and what Jonathan got. I divided it by an incorrect denominator. So let's say this is further away, expiring in 200 days, expiring in 100 days. So let's see what's the difference between if expire in 100 days, if expire in 200 days. So now we can see how this discounted strike price change. So now we see that given this, if time to expire increases. So okay, that's what Codex says. It says that it decreases, but I'm having trust issues here. So let's do a comparison here. So given the following variables, k equals to 40, t is equals to, sorry, r is equals to 0.01, this is the risk-free interest rate, 1%, then we can see that if it expires in 100 days, like longer, then it, yeah, okay, so it does decrease. But why? So we were able to understand how discounted strike price behave empirically by testing the formula out. So, I guess that makes sense, because if we are intuition behind why the discounted strike price, what is the intuition behind why the discounted strike price decreases with time, increasing time to expiry. My hypothesis is that if the option is exercised in a longer time, we have the current value, we will get $40 with a lower amount discounted strike price. If we get the risk-free interest rate for the time we have to wait. For the intuition behind why the discounted strike price decreases with increasing interest rates, if the option, if the interest is higher, we will get $40 with a lower amount discounted strike price after, if we loan out the money we have for exercising the option for the time we have to wait. So in summary, both the risk-free interest rate and the time to expiry both increases the interest that you would get by loaning out the money that you would use to exercise the strike price in maybe 100 to 200 days. And that is why if we discount the strike price, the current value of that $40 that you will pay for exercising that call option will be lower given a higher interest rate or a higher time to expiry. So that makes sense to me. I might be wrong, maybe I'm missing some details here, but it's okay, let's figure this out later. So let's continue with Jonathon's video.
Excellent. So now I would say,
okay, but to be sure that the typo that we did in T here, we divided by 375 earlier, we should have divided by 365, and the answer that Jonathon got was 0.51 for the fair price of call option. Yep, we got 0.51. And if we round this to 2 decimal places, then we should get 0.51. There we go.
say else, but let's just else if type is equal to P, is parameters above. So we've actually called them exactly by the name, so let's just copy and paste them. Okay. And because we're using the round function here, we're going to round 2 decimal places. Finish off the brackets, save that down. Now in our terminal here, we're going to type Python Black Scholes py, and we're just going to hit run. Oh, and no module SciPy. So for any of you that have that, we're just going to pip install those modules. Super easy. I just didn't have that in this environment. But NumPy must have been there. So we'll just wait for that to install. And then we'll be able to run that again. So just up key, enter. Excellent, option price is 51 cents. And if you remember from the Excel video, that was about similar with that, despite the fact that we missed out the T. And that's because it was close to 1 year. So, you know, we're timesing by 0.6, 0.7, and it's maybe a very small number anyway. 0.3 squared divided by 2, it's kind of a small number. So timesing by 1 or 0.6 doesn't really make a big impact. So let's see what happens when we change this to put. We're going to save that, and 10.25.
Let's test it out as well. So fair price of call option. And let's print out the fair price of put option as well. So this put option here should be 10.25. So credits to Quantpy. Please watch his video here. So here, there we go. Okay, let's print out this put option, but instead of passing in the call here, instead of defining the variable above, I'm just going to pass it at where we call the method. So it's 10.25. Yes, we got it right.
So very, very similar there. So we're going to try and add it and create a dashboard in further videos so we can make this more interactive. Excellent. So thank you very much for listening, guys. This is ASX Options, and if you like the video, go ahead and subscribe so you get more content, and hit the like button.
Okay, thank you so much. This is great. Like, personally, I have never touched the Black-Scholes model in depth before, and as you can see, I was really shaky with my intuition behind discounting the strike price. We haven't talked about the other terms as well, like how does this term change, what does this term mean, what does the natural log of current price to strike price here mean. This is the numerator, it affects the numerator, and D1 eventually affects D2 in a positive way as well. So D1 and D2 are positively correlated, if I'm not mistaken. But for the purpose of this video, I think it's pretty decent. There are some things that we can cover in a subsequent video. For example, going through how exactly this price changes with respect to other terms as well. So we saw how the discounted strike price changed with risk-free interest rate and current stock price here. But we haven't talked about the overall effect of how time to expiry affects the price in general. So I think it's a pretty good exercise nonetheless, and I hope you enjoyed this. I'll be uploading this to GitHub so that you can take a look at this as well. And thank you so much for watching, and we'll see you in the next video.